Hey, Haley. Come on in, everybody. About 3 minutes before class begins. Feel free to ask me any questions you might have. Another one. All right. Looks like we got about 7 people. So, anybody have any questions while we're waiting? We got about 1 minute before it's time to start. Hopefully, you all got my email that we pushed the lab back. I mean, the exam back. So, we're not taking it until a week from today instead of today, or I guess you would have took it just before class. For some reason I was thinking, actually, y'all have lab after this, right?
Yes.
Thought so. Thanks, Randall. All right. Well, it's essentially 5:20 now, so I guess I'll go ahead and get started. We've got a little bit left to finish up on the chapter we're working on, which I want to say is chapter 25. And I'm going to double check that, but I'm about 99% sure that's the case. But I am using like 4 or 5 different books, so it's always a question when I say what chapter, because literally the same chapter is a different number in other textbooks. But I'm thinking it's 25, and we're going on to 26 next. And the answer is chapter 9. No, that's not right. That just happens to be the chapter that I left it on. So, ooh, no, it was chapter 26. My fault. So yeah, it is chapter 26 that we're finishing up on. And at this point, we are working on uh, basically circuits. So Kirchoff's rules and stuff of that sort. I'm not really skipping it in the sense that you're not required to do any material from 26 core. I'm just not covering it. The examples are straightforward. The reading is straightforward, but I am going to do a Kirchhoff's law problem. So you will definitely see how that works. And I'm going to give you a general method that you can use. Actually, I'll give you 2 general methods that you can use to solve the system of equations that occurs as a result of this. So we're working on section 26.3, but in reality, we're covering sections 26.3, 26.4. And then we're going to RC circuits, capacitor charging, capacitor discharging, and ultimately I'm going to teach you how to make a galvanometer into an ammeter and teach you how to make a galvanometer into a voltmeter. So that's the last parts of chapter 26. And if I remember correctly, I think I actually said our exam only goes up through 25. So let me double check just to make sure of that. So this stuff will not be on it. I'm going to double check so I'm not telling you the wrong thing. And it looks like, oh, good. I went ahead and wrote the practice test, but neglected to write what chapters it covers. Looks like do go through 25. Let me double check the actual questions to see if my wording is right. Yes, it's only through 25. Okay, so I'll ask one more time. It's actually time to start class, but does anybody have any questions on any past problems, material, or anything like that that you might be having problems with? Otherwise, I'm going to just start cracking in on this. All right, not seeing any chats put up. Okay, so what we're starting off with is basically last time you saw me compute the voltages at various places in a circuit using that sort of bubble method that I told you about, where you sort of are, one thing you're always allowed to take in a circuit and put the ground anywhere you want. What I normally do if I ever do that is I'll take the largest power source, in other words, the largest voltage battery, and I'll stick a ground on the negative side of that and just literally draw a little line and then draw a straight line, a shorter straight line centered on the same line, a shorter straight line centered on the same line, and then a dot. That's the symbol for ground. So I'll write that right on the backside of it. And then that point, we know the voltage is 0. So if you take the black COM port on your voltmeter and stick it there, or alternatively stick it in the little mouth looking hole in the light receptacle, that's also ground. And then you go around and poke the red probe that goes in the V omega slot on the voltmeter. Those bubbles are telling you exactly what the voltage is. Now, if you are actually using the mouth holes in the light receptacle, then there is some chance that you're not necessarily getting 0 at where I would put it at 0 in the bubble. So for instance, the negative side of the largest power source would not necessarily be 0 volts. You can do all sorts of weird things to make that not be that. So just be careful. I rather just picture putting the ground on the negative side of the biggest voltage battery, and then I'll put a bubble there and say that's 0 volts. And then you can just imagine I'm holding the COM terminal from the voltmeter. I'm holding it on that spot, and then all those bubbles are what I read when I touch the particular spot that bubble is connected to with the red terminal. So hopefully that'll help you. But that's sort of what I call a higgledy-piggledy way of solving a circuit. There's a more actually, there's multiple ways that are a little bit more reliable and algorithmic. So what we're going to learn is one of them. If you look on my YouTube channel, and on the videos that I've posted on your Canvas page, you'll see there's a method called the nodal method. That's another nice one that works. And there's another one called the loop method that I didn't choose to do it because I didn't really care that much for it when I covered it. But what we're going to do is just go with Kirchoff's junction rule and Kirchoff's loop rule and use that. So let me go ahead and share my screen. Anybody have any questions before I jump into this? I'm gonna go ahead and share the screen. I can answer the questions even if you happen to. It looks like nobody's chatting anything, so that's a good sign. Looks like no one has any questions. So that sounds cool to me. I've moved this over here. I'm getting rid of this. Oh, another student came in. I have no idea what's going on with that. Okay. All right. So what I've written here is a graphical representation of Kirchoff's rules. So Kirchoff's rules, by the way, if you've ever had a course in astronomy, there's also Kirchoff's laws, and that's the same dude. So Kirchoff's laws tells us why we see continuous spectra, why we see absorption spectra, and why we see emission spectra looking at different things. That's Kirchoff's rules in astronomy. Here we're doing basically two things. In Kirchoff's junction rule, which I call it KJR, some people call it junction law and they call it KJL. I pretty much use R on it on all of them. But basically what he's saying in Kirchoff's junction rule is the sum of all the currents into a circuit. So the sum of all the currents into a junction, so that's I1 plus I2 plus I6 plus I7 is equal to the sum of all the currents out of the junction, which would be I3 plus I4 plus I5 plus I8. So that's Kirchoff's junction rule. And Kirchoff's loop rule, by the way, Kirchoff's junction law or junction rule is just a conservation of charge. If you imagine the number of charges that come to that junction in a single second, then what are actually the amount of current that comes to that junction at a single second, then basically you're taking the amps, which is coulombs per second, and you're just getting rid of the second part. So it's a certain number of coulombs comes in I1, I2, I6, and I7. And that same number of coulombs has to leave the junction, which is I3 plus I4 plus I5 plus I8. So that's just a conservation of charge. Similarly, if you remember, sorry, I'm trying to do 15 things at once here. So it's probably best not to say sentences while I'm trying to write words that aren't related to the sentences. So anyways, with regards to Kirchhoff's loop rule, that's actually a conservation of energy statement. And that is easier to see if you think about voltage. If you remember how we defined it, that was actually the negative of the work done by the electric force divided by the charge. So it's literally an amount of energy per unit charge. So in that sense, you should say, oh, voltage is really a energy per coulomb. And in fact, if the energy goes up and then down and then up and then down and you complete one loop, what that means is you've gone from one place to the exact same place, and it'd be crazy to have a different energy level. So sure enough, what that means is if you take all the voltage drops and all the voltage increases in a single loop in a circuit, the sum of all those, once you finish the loop, will be equal to 0. So that's conservation of energy that we're talking about here. So now there's some rules about that. And what I want to tell you is I'll do it graphically again. And this is really the most important part with Kirchhoff's loop rule. Basically, if you are traversing, okay, let's say you traverse this way. In other words, you've chosen a loop and you're following the path in that loop, and that path requires you to go this direction, okay, then what's going to happen is the following. For instance, if you have, oops, I did not want that color. So if you have a wire and then a resistor, and you say that in this particular circuit, that current is going this way, okay, then this right here is a voltage drop. Now, if you get to another part in the circuit, and this time the current's going this way, ooh, I don't want to draw it that way. This time the current is going this way, then this is a voltage increase. Also, oops, I did not want that color. If you run into a battery and it's oriented that way, this is a voltage increase. And if you traverse a battery, oops, again, wrong color. If you traverse a battery that's oriented this way, then this is a voltage drop. So that's the rules that you got to make sure you stick to when you're doing Kirchoff's loop rule. If you don't stick to it, you will get errors. Okay. In other words, you won't get the right answer. So let's go ahead and apply that for one particular circuit. And you've got, like I said, this is a example. Your book has another example that's very much like the example I'm getting ready to work. Your book has a example with a circuit where you're charging a car battery, and that teaches you some valuable information about charging a battery, how to connect the battery, as well as what happens if you connect it backwards and all that good stuff. And then in my Canvas course, you'll see there's numerous videos that I posted where I'm solving circuits in my YouTube channel. So you can also check my YouTube channel, or you can go straight to your Canvas. But there's a ton of them for you to look at. So let's do this first. So what I'm going to do is I am going to say that this current right here is I2, and it's going down. I'm going to say this current right here is I1, and it's going up. And then this current right here is I3, and that's going to the left. Now, I didn't do 1, 2, and 3 in the normal order, and that's because I had already planned out what I did before. So I just started writing in the most convenient place. So first thing I'm going to do is Kirchoff's junction rule. And I'm going to do it for this point right here, A. So I'll write for junction A. Now you'll notice there's actually another junction here that's B. In fact, the rule is if you have two junctions, one of them's useful, the other one's just a repeat. If you have three junctions, two of them's useful, the other's just a repeat, and so on and so forth. So you're always going to use one less than the number of junctions you have. So in this case, you'll see that I3 is coming in and I2 and I1 are coming out. So the actual junction rule that we get here is I3 is equal to I1 plus I2. And I'm going to call that equation 1. Now I'm going to apply Kirchoff's loop rule. And this one's for the bottom loop. Okay, so the bottom loop means basically the middle line that goes with the I3 on it and the bottom part that goes with the I2. And specifically, I am going to start here and go this way. Okay, that's how I'm doing my loop. So if I start here, notice at A, if I start at A, then the first thing I run into is a 40 ohm resistor. But that 40 ohm resistor, I'm traversing it in the opposite direction of the current. So according to my rule, that's going to be a voltage increase. Then I'm going to run into a 41 ohm resistor. So basically what I'm going to get is 40.0. Remember, V equals IR from Ohm's law. So if you multiply I3 times 40, you get the voltage. And in this case, it's a voltage increase because I went the opposite direction of the current. Then I got another voltage increase, which is 1.0 times I3. And then I've got in this case, I'm going from the long line of the battery to the short line of the battery. And in that case, it's going to actually give me a voltage drop. So this will be a minus 50.0. And now I've got to point B and I'm going down. This time I'm also going against the current because I2, you can see, goes basically sort of counterclockwise around that bottom circle. So going opposite direction of the current, I've got again a voltage increase, which is going to be plus 20.0 I2. And then I've got a plus 1.0 I2. And then finally, I get to the 90 volt battery. And in that case, I'm going from positive to negative again. So this is also going to be a minus 90.0 volts. Now I can simplify that, and I will before I number it. So I can combine the 40 and the I3, and I can combine the 20 and the I1. And what I'm going to, or excuse me, in the I2. So what I'm going to have is 21.0 I2 plus 40, 1.0 I3. That takes care of this one, and this one, and this one, and this one. And so now I've taken care of those terms. And now I've got minus 40, or excuse me, minus 50. And for some reason I wrote plus 90. That's supposed to be minus 90. Let me correct that real quick. Again, that's a minus 90 because as the red arrow shows, I went from the long side of the battery to the short side of the battery. So this should be negative 90 plus negative 40, negative 50 is negative 140. So I get minus 140 is equal to 0, and that's going to be equation 2. Okay. Now I'm going to do Kirchoff's loop rule again. And this time I'm going to do the outer loop. Okay. So, and I'll go the same direction. So in this case, let me draw, I want to do a different color other than red. Let's do this. So this time I'm going the outer loop. I will start right here and go around this way. Okay. And I'll put a green arrow here, and I'll put a red arrow here so you know which one corresponds to which. Now I'm going back to my blue, and now I'll start at junction A, and notice this time, because I'm going up and to the right, I'm going the same direction as I1. So the 30 ohms is in fact a voltage drop. So I'm going to say minus 30.0 times I1. And then I get all the way back down to the 20 ohms. And this time I'm going against the current. So it's going to be plus 20.0 I2, because that's a voltage increase because I'm going against the current, plus 21, or excuse me, plus 1.0 times I2. Again, that's a voltage increase because I'm going against the current. And then I go from the long side of the battery to the short side, which means that's a voltage decrease. So I'll say minus 90.0. And now I'm back where I started from. So I say equals 0. And now I'm going to get this in, I'm going to simplify it and combine like terms, in other words. So I've got 30I, I've got 21, or 30I1, I've got 21I2. So I'm going to say 21.0 I2 minus 30.0 I1 minus 90.0 is equal to 0. And that's going to be equation 3. Now, I will tell you that the most straightforward way to do this, but quite time consuming, is to actually use like one of your matrix methods. I'll show you after all this is done how you could do the matrix method, and then your calculator can actually do the matrix stuff for you. I don't want you using that. You should be able to do, you know, at least 2 or 3 of these by hand before you ever try just doing it with the calculator. But I highly recommend every time you do it by hand, you check your answers with the calculator or with an online matrix calculator or something like that. So I'll introduce that in a second. So the first thing I'm going to do is I look at, and this is what I almost do, I do almost all the time. The way I drew these circuits, I know, for instance, that equation 2 has current 2 in it and current 3 in it, and equation 3 has current 2 and a current 1. So what that means is I can express current 2, or excuse me, current 1 in terms of I2, and I can express current I3 in terms of I2. If you can ever do that, if you have 2 of your equations and you can get one of the currents in terms of, let's say in this case, I2, and then the other equation also lets you get another current in terms of I2, then you can use that to plug in the junction rule, and you'll have nothing but I2s. So you'll have one unknown, one equation. That's what we're going to do. So that's really a surefire way to do it. So if you just try to choose the loops so that one equation allows you to solve for a current in terms of a very specific current, and then the other equation allows you to solve for another current in terms of that same specific current, then that's the way to do it. So I'm going to first take equation 2 and say solve 2 for I1, or excuse me, for I3. And what I'll get is equation 2 prime, which I'm going to call, we're solving it for I3, and I3 is going to be in terms of I2. So what I'm going to get is I3 is going to be equal to 140, because when I put it on the other side of the equation, it becomes positive, minus 21.0 I2, and now I've got to divide it by 41. And now what I've found super useful is go ahead and divide out that fraction. So 140 divided by 41. Make sure I'm dividing by the right thing. I did. 41 was the coefficient of I3, so that looks good. And 21 was the coefficient of I2, and that's a negative, so that's good. So 140 over 41 is 3.415, or 4146. 4146, like that. Notice, by the way, in doing this, that's 3 sig figs divided by 3 sig figs. So this is giving me 2 extra sig figs, just for the record. And now minus, I take 21 divided by 41. That's 3 sig figs divided by 3 sig figs. This gives me 0.51220. And that's times I2. And again, that's 2 extra sig figs. So that's going to be my equation 2. Notice it has an I3 in terms of I2. That's really helpful. Now I'm going to solve equation 3 for, in that case, equation 3 has I1 and I2. So I'm going to solve it for I1 in terms of I2. So notice that the important thing is the current it's in terms of. So it's not necessarily that important which current I'm solving for, but what's important is what current is on the right hand side after I solve it, because if you can get the same for 2 and 3, then you're golden. So this is going to be equation 3 prime, and this case is I1 is equal to, so if you look at I1, if I pull it to the other side, it becomes 30 I1. So I'm going to do that, and then I'll have 21.0 I2 is positive, minus 90.0, and then the coefficient of I1 is 30. So I'm going to divide by 30.0. Again, I'm going to go ahead and do the division. 21 divided by 30 is 0.7. And of course, that's all 0 after that. And 21 divided by 30.0 should actually be 3 sig figs. So I'm carrying 1 extra, but it really doesn't matter too much because we know that all the other digits are 0. And then I've got I2. And then 90 divided by 30 is just 3. So that's going to be minus 3.00. And again, that's just 3 forever. So I can just put that after it, and I've got an extra sig fig on everything. Now I'm going to plug 2 prime and 3 prime into 1. Okay, now you can look back at the notes, and this is why I keep track of this stuff. This is why I have all my equations numbered. I have 3 unknowns, I1, I2, I3, and the rules of algebra, the fundamental theorem of algebra, essentially says that if you have 3 unknowns, you have to have 3 separate equations, 3 different equations. And therefore, if I've managed to solve for 3 unknowns with only using 2, then I've done something that can't be done. But by numbering them and looking through my record, I see I've used 2 and 3 already, and I'm getting ready to use 1. I now know I've used all the equations. So any mistakes that happen are my own. So what I have is I3 is equal to I1 plus I2. Well, we already said that I3 is given by 2 prime. So I'm going to say 3.4146 with 2 extra sig figs minus 0. Actually, I'm going to write that below that. I just don't have enough room there and I'm writing it too small, and that's going to make it hard for you guys. So I'm going to say 3.4146. Okay, minus 0.51220 I2. So that's I3. And according to the equation, I3 is supposed to equal I1 plus I2. So I1 is, of course, given by 0.7000 I2 minus 3.000 and then plus I2, which is again from equation 1. So now you see you've got exactly one unknown. It's specifically I2. So I'm going to combine all those like terms. Notice on the right, I've got 0.7 I2 and I've got 1 I2. So it's best to pull the 0.51 over to the right. And what I'm going to do is I'm going to pull the 3.0 over to the left. That's going to give me 6.4146 on the left-hand side. That's taking care of this guy because it comes positive over there, and it is positive there. And now I'm going to add 1.7 because when you add the 0.7 and 1, you get 1.7. So I'm going to say 1.7 plus 0.51220. That's going to give me equal to, oops, wrong color. Hate when I do that. That's going to give me 2 point, that's going to give me 2.21220 times I2. Okay, so now all I got to do is divide both sides by 2.21220 divided by 2.21220. So the left-hand side, you got 3 sig figs divided by 3 sig figs. That gives me 6.4146 divided by 2.2122. That gives me 2.8996. And that's supposed to be 3 sig figs, so that 9 and 6 is extra. And then on the right-hand side, I just have I2. So that's supposed to be current 2. And notice I didn't put much thought into which directions I1, I2, or I3 were. Well, I just wrote them down for you guys, but I really didn't put much thought in it. The main thing is if you choose the wrong direction, it's not going to harm you at all. But when you solve for the particular current, it'll come out negative if you chose the wrong direction. And that's fine too. You just got to remember to continue to use the negative for the remainder of the problem so that you get the right answers, because it's got to be negative in all the other equations as well. So I've now gotten current I2, and that's part of the goal. As you might have suspected, the goal for this is just to solve for the currents, I1, I2, and I3. So now that I have that, I have I2, which is luckily exactly what I3 and I1 are in terms of. So now I can say I1, and this is from 3 prime. So I1 is now equal to 0.7000 times 2.8996 minus 3.000, which gives you I1 is equal to, let's see, 0.7 times 2.8996 minus 3. That's going to give me negative 0.9703, which is carrying 1 extra sig fig, and that should come out in amps. This one should have come out in amps as well. So we did choose the wrong direction for I1. So I1 is actually not going up and to the right. It's going to the left and then down on the left-hand side. So we've got that now. And then now I'm going to take equation 2 prime, and that's going to allow me to find I3. And according to it, I3, that's just ugly. I'm just really bothered by that. Sorry. I3 is supposed to be equal to 3.4146 with the 4 and the 6 extra sig figs minus 0.51220, which has that extra sig fig. I actually marked too many extra sig figs on the other one. No, actually, I didn't write enough. That's what it was. Oh, no, that's what it was. I got you. Okay. So it's that times I2, and I2 was 2.8996. Again, with extra symbols, this says I3 should be equal to 3.4146 minus 0.51220 times 2.8996. And this gives me 1.929, which is 1 extra sig fig amps. So I'll underline that extra sig fig, and that's our actual currents. Okay, so that is really a way you can do it. If you chose to do something else or a different way, what you could do is write these equations, I1, I2, I mean, equation 1, equation 2, and equation 3 in a very specific way. So let me show you what I'm going to do with that. Let's see if I can add another page here. Let's see, paste page, what happens? All right, so I just pasted a page after that. That's cool. So what I'm going to do is I'm going to rewrite equation 1. So to solve using matrices. Okay. First off, equation 1, I've got to change that a little bit. And the main thing is, if you're using like Gauss-Jordan method, which is where you do row and row operations and combine them until you get 1 0 0 0 1 0 0 0 1, then the last column of the 3-row by 4-column matrix will be the actual answer. So the last column would be the answer for I1, then the answer for I2, then the answer for I3. So you could actually write this that way. And in this case, it's going to become I1 plus I2 minus I3. So this would be I1 plus I2 minus I3 is equal to 0. So that's one way you could do it. Again, if you make it a 4-column matrix, that's for Gauss-Jordan. So 4 columns. Oh, I just wrote coulombs. That's funny. So 4 columns. Okay, but you can do 3 columns, and then you can use what is the name of that rule? Anybody remember the name of the rule? Kramer's rule. Okay, so let me show you again what you're going to do with that. So first off, we got to rewrite these equations. Now I'm going to rewrite equation 2. And equation 2, we found out, was 21 I2 plus 41 I3 minus 140. In this case, I want to write 0 I1 plus 21.0 I2 plus 41.0 I3 is equal to 140. Okay. And notice that Z has to, that 0 term has to be there. Now I take equation 3, and that was 21I2 minus 30I1 minus 90. So I'm going to write minus 30I1 plus, and actually I technically should do, let me write this correctly so we can keep track of sig figs. Minus 30.0I1 plus 21.0 I2, and make sure that was right. That was 21.0, wasn't it? Yes. And then there is no I3 in this one, so we're going to have to put plus 0 I3. And then all that is equal to 90 on the other side. So notice I just wrote all the same equations. I just wrote them very specifically. So if you want to use Gauss-Jordan, what you're going to do is take this matrix, which is going to be 1, 1, negative 1, and 0, 21.0, 41.0, and this last column would be negative 30.0, 21.0, and 0, and then over here you'd have 0, 140, and 90.0. Okay, and you slowly transform that into 1, 0, 0, 0, 1, 0, 0, 0, 1, and what would happen is you'd get negative 0.9703 and 2.8996 and 1.929. So that's what would happen if you did the Gauss-Jordan method. And these, this is just a way of breaking up the matrix of the terms from the matrix of the answers, or the column of the answers. So that's the Gauss-Jordan method. That way would actually work. But if you wanted to do Cramer's rule, what you would do, what you would do is you'd say I1 is equal to the determinant of the x, which I'll explain in a second, divided by the determinant of d. I2 would be the determinant of y divided by the determinant of d, and I3 would be the determinant of z divided by the determinant of d. And what d is this vector. Now, technically, I'm saying d is the determinant. So d means the determinant of the following matrix, which in this case, I'm just going to put the matrix of the equations, which would be 1, 1, negative 1, 0, 21, 41, and negative 30, 21, 0. dx would be the determinant of this matrix, where basically it's the same thing you did just then, except I'm going to take that first column and replace it with the answer column. So I'm going to go 0, 140, 90, and then I'll do 1, 21, 21, and negative 1, 41, 0. dy would be the determinant of, now we're going to take the original first column and turn that back to what it was, which is 1, 0, negative 30. Now I'm going to replace the second column with the answer column, which would be 0, 140, 90. And then I'll leave the last column, which is negative 141, 0. And then finally, dz would be the determinant of this matrix, which again is 1, 0, negative 30. So we haven't changed the first column. We haven't changed the second column. So that's 121, 21. And the third column we have changed, and that's going to be 0, 140, 90. So if you calculate those determinants independently, which your calculator can do in most cases, then you're going to actually get the right answer. So I'm just going to put in here and here. Oh, not there. And here, just so you'll recognize that's the same as what was in here. So that is a brute force way that will always work. It's not necessarily the most time efficient, but in the long run, it's always going to be the most time efficient, because you're never going to, you're not always going to find an easy way when you just look at it. So if that's not the case, if you can't set it up like I did, where you can solve equation 2 for one current in terms of I2, and you can solve equation 3 for another current in terms of I2, then you can plug that all into equation 1 and only have one unknown, i.e. I2. If you can do that, then yeah, that's more efficient and that'll work, but it's not always that easy. So anyways, hopefully that'll help you guys in solving systems of equations and in checking your own answer. Anybody have any questions on how this was done? All right. Doesn't look like anybody chatted anything. Okay, so we'll move on then. So if you need any help on the matrices stuff or whatever, let me know. Or you can just Google it. There's a lot of good sites. There's actually websites that do matrices computation for you as well, so you could actually try it with this one. You might want to see if I didn't make any careless mistakes. I don't think I did, but there's a possibility. The bare minimum, by the way, when you solve a system like this, is at least go back and see if the Kirchoff's junction rule is right. So if I took 2.8996, and that's I2, and I added to it I1, which is minus 0.9703, that better give me what I3 is, and I get 1.9293. So yeah, even to the non-sig fig, it's actually right, because I get 1.929, and that last 9 is insignificant. So it's amazing that I got even that right. So that's sort of the bare minimum that you want to check. But ideally, what you want to do is put it in your calculator and see if the matrix gave you the same answer. Of course, you have errors that could pop up in putting the matrix in as well. So anyways, all right, let's look at charging a capacitor. So this is charging a capacitor. Now you can look at my YouTube channel to see the derivation of this, but basically we can use Kirchoff's loop rule to calculate the change in voltages for each of these elements as we go around the circle. Of course, we have to use V equals IR to find the voltage drop across the resistor given the current I. And of course, the current I specifically means it's going this way when you first close the switch. So you'd have V equals IR as a drop across the resistance, but then you'd have V equals Q over C as a voltage drop across the capacitor, and then you'd have E as a voltage increase in going around one loop. And then you could do things like I is dq dt. However, sometimes you might find that I is negative dq dt, because if the current is coming at the cost of the charge on the capacitor, then the capacitance loss is the current's gain, so you use a negative. But the main thing is, once you have that, it's a differential equation in terms of Q and derivatives of Q. And ultimately what you get is the following answers, and you're just going to use these. So the answers are the voltage across the capacitor is actually, if you let the current run, so what's going to happen when we first close that switch, the positive side of the battery is going to compel the positive charges in the wire that are free to move because it's a wire, i.e. a conductor, that's going to compel those charges to flow around this circuit in a clockwise fashion. As that current goes through the R, the voltage drop will be the whole voltage of the battery, which is E. Okay, it's that EMF. But what's going to happen is you'll slowly build up a charge of positives on this left-hand side. Those positives will compel the positives on the right-hand side to run away, and those positives will, in fact, return back this way. But what's going to continue to happen is as that charge builds up higher and higher, that makes a larger and larger voltage until basically the voltage across the capacitor is the entire EMF E, and there's no voltage drop across the resistor because the currents come to a stop. So you expect the current to fall off to zero. So the voltage across the capacitor, when you solve this differential equation, is going to become E times 1 minus E to the negative T over RC. And I'm going to tell you that tau is defined to be the time constant for an RC circuit. And as an extra credit, you can show that RC units are equal to seconds. Okay. Now, the other part you'll get, and this is a useful equation that we're going to make use of in a second with an example. Another equation you can get is that the charge on the capacitor, Q, is going to be equal to basically, if you take V or you take C equals Q over V and solve for V, what you get is V equals Q over C. But if you take it and solve for Q, you get C times V. So what we're actually going to have here is E times C. And then times the exact same expression, 1 minus E to the negative T over RC. So that's the equation for the charge on the capacitor at any time T. And then, as I told you, the voltage and the charge on the capacitor are slowly ramping up to some maximum value, but the actual current starts off kind of high, like it's nothing but a resistor there, and then it's going to fall off to nothing. And because of that, we get an equation for the actual current that is I is equal to. Now, if the battery was just running a current through a resistor R, then the current would be V over R. So this is going to be E over R like that. And then that E over R will be multiplied by E to the negative T over RC. So that's what the equations for charging a capacitor are. And you could actually look at the graphs as follows. Oops. Let's say this is time. Let's say this unit of time right here is tau equals RC. And this is going to be VC. So the voltage across the capacitor. And what you'd see is that we're going to have a value right here of E. And that's actually going to be what's called an asymptote. And the actual graph would look like this. Okay. Now you could also make a graph of Q, and this one I'll make blue. And in this case, instead of E, we'd get EC is that value, and the graph would be identical, asymptotically approaching, in this case, E over C. Okay. Now, the big thing is if you take and look at T equals RC, then you'd get e to the -1. And if you compute what e to the -1 is on your calculator, I hit second function len -1, and I get 0.3679. So just as a sidebar, I'll put this here. E to the -1 is equal to 0.367. It's actually 87, but I'm just going to call that 9. Okay, it's a number that never is irrational. Let's put it that way. So that's really what it's going to be. But what we have in V and Q is 1 minus that. So if I do 1 minus that, I do 1 minus that, I get 0.6321. So 1 minus e to the -1 is equal to 0.6321 approximately. So what happens here is if you go up and then hit the graph and then come over horizontally, this is 0.63 times either E or EC. Okay, so what that means is after one time constant, you get 63.2% roughly. Okay, now the other graph is the graph for I, and you probably know what that looks like, but I'm going to draw it anyways. So let's draw it here. And I always forget to change that. This is T. This is I. Of course, the in this case, it's not asymptotic. It's not an asymptote, but it's actually going to start off at T equals 0, being just plain E over R. So this quantity right here is E over R, and it's going to drop down exponentially like this and sort of asymptotically approach 0. And again, what we're going to have here is a time constant, tau equals RC. And in this case, it's going to be 0.36, let's call it 37, E over R. Any questions on that? All right, so I want to break that off a little bit. I still need these little facts about E, so I'll leave them outside of the green box. And now what I'm going to do is I'll say right here, and what we're going to do is work out the same problem for discharging a capacitor. So this is discharging. Ooh. And what we're going to have for that circuit is essentially, you can imagine having a battery still in the circuit being able to charge the thing up. But what you can do is imagine instead, we also have a second route for once you've got it charged up. I'm going to do like this and then show the switch goes through both of these like that. And then this wire will go up here to a resistor R and to a capacitor C. And since we're discharging, we're going to say that this capacitor has a charge Q0 on it right there. Okay, so that's the circuit we're actually going to use, but I'm going to go ahead and use the equations that we just that I just gave you to find out to actually solve a problem. Then I'll come back and give you these equations. So let's start on this equation right here. Does anybody have any questions before I go on with this? Oh crap, we only got like 4 minutes. That's, oh no, we got 24 minutes. Ooh, that's a lot better. Okay, so what we're doing here is charging a capacitor. So I'll just write here charging a capacitor. So we have the same circuit that I just drew in the first part, not in the second part, only we have capacitance is equal to 0.6 microfarads, R is equal to 20.0 kiloohms, and E is equal to 12 volts. And we're asking for all these questions. So what I'm going to do is say solution, and I'm going to solve it. Okay, so part A, they want to know tau equals RC. Well, that's 20.0 kiloohms. In electricity, specifically electric circuits, a lot of time we don't convert back and forth between kilos and millis and megas and micros and all that good stuff. We just treat them as is, and I'll show you what that means in this particular case. I'm going to say 0.60 microfarads. Now, a micro is like 1/1,000,000th, and a kilo is 1,000. So if you take 1,000 divided by 1,000,000, you get 1/1000th, which is a milli. So that's a millisecond that's going to pop out of here. If I multiply 0.6 times 20, I'm basically multiplying 20 times 6/10. So if I first divide 20 by 10, I get 2, and then I multiply that by 6, and I get 12. So in fact, the answer is 12.0 milliseconds with 1 extra sig fig. So don't feel obligated to do that rigmarole with the various prefixes. You can go ahead and convert it to 10 to the third and 10 to the -6, and then write your answer, and then maybe convert it back to milliseconds if you want. That's all fine. I'm just trying to show you another way you can do it as you become more skilled. Now in part B, we want to know what is the maximum charge that Q will get. And we sort of know that already, right? Because the maximum charge Q will get is the Q that occurs when the voltage across the capacitor is the entire voltage of the battery. So using C equals Q over V, we know that Q max is going to equal C times E. So all I have to do is say Q equals C times Z, that's 0.60 microfarads times 12.0 volts. And again, this is 0.6, which is 6/10. So I could divide 12 by 10 and get 1.2, and then multiply that by 6, and I get 6, and then 1.2, so that'd be 7.2. So this should be 7.20, keeping 1 extra sig fig, micro coulombs. So notice in that case, I only had 1 prefix, and I just kept the prefix. So that's what Q max is. Anybody have any questions on that? Now for part C, they want to know at what time will Q equal 99% of the Q max. So we're going to do that now. We'll say C, if Q of T equals 0.99 Q max, what is T? That's really what we're asking here. So in this case, remember the Q equation is what we're employing. So I'm going to write down 0.99 times C times E is equal to C times E times 1 minus E to the negative T over RC. Doing that, I can see that the CE's cancel out. And now I can pull the negative E, because once I canceled out the CE's, this thing in parentheses on the right is no longer in parentheses. So I'm going to pull the negative E to the negative T over RC to the left. That's going to give me E to the negative T over RC on the left. And it's going to give me 0.01 on the right. because I'm taking 1 minus 0.99. Now, with that, what we do is I take the natural logarithm of both sides. So I'm going to say the natural logarithm of e to the negative t over rc is equal to the natural logarithm of 0.01, like this. And actually, like that. Okay. At this point, I can get that e, the len of e. One thing that'll really help you, and this has been the single most valuable logarithm fact I've ever learned, and it's y equals log base b of x implies, and that's a double arrow, x is equal to b raised to the y power. So looking at that, I can see that basically the natural log of e to the negative t over rc is just negative t over rc times the natural log of e, which is in fact just 1. The natural log of e is just 1. So that's the part that I see from the green expression I wrote here. So I'm going to now say negative t over RC is equal to the natural log of 0.1, so, or 0.01, excuse me, and the natural log of 0.01 is negative 4.605. Okay, so what this tells you is that t is equal to 4.605 time constants. And I had a student in my previous class told me that you basically assume there's 5 time constants before the entire charge is gone or the entire charge is filled up. And this is confirmation of that, because 4.6 should round to 5. But anyways, you should assume that when they say at what time, they're actually wanting seconds. So I'm going to actually go ahead and compute this in seconds. So that's going to be 4.605. And technically speaking, you really only have 1 sig fig to work with. So all of these guys are non-sig figs, which really stinks. And then we're going to multiply that by tau, which is 12.0 milliseconds. So if I take 4.605 and multiply it by 12, I get 55.3 milliseconds. But again, technically with sig fig rules, I'm only supposed to have that as roughly 50 milliseconds. But I'm not about to write an answer that's stupid, so I'll just leave it here. Any questions on that one? This was answer B, and this was answer A. All right, so we got C, and now D is what is I when Q is equal to half of Q max. So for this one, we're going to try to figure out what I is when Q is equal to Q max. In order to do that, we need to know what time that occurs. So I'm going to start off by doing that problem. So this is part D, and what I'm going to say is Q of T is equal to, remember the max Q is EC or CE times 1 minus e to the negative t over RC. That's the whole Q of T function. What we want to know is what is T when Q is equal to 1/2 EC. So we get EC times 1/2 is equal to EC times 1 minus e to the negative t over RC, which I think now you can tell enough from what I did before that this is going to be basically e to the negative, I should use red. This is going to be e to the negative t over RC is equal to 1 minus 1/2, which is 0.5 and you can use any number of sig figs on that 1/2, really. So now that we have that, we can take the natural log of both sides, and I'm going to get negative t over RC times the natural log of E, which we already know is just 1, is equal to the natural log of 0.500. And of course, everybody should know that that is negative 0.629. If we take the natural log to double check that, you can say the natural log of 0.5 is, excuse me, I said 6.29, it's 693. So in this case, this is negative 0.693, and it's 1 is the next digit, if I remember. Yeah, that's correct. Okay, so that's what we get here. This actually implies ultimately that T is equal to 0.6931 times RC, which means basically 0.693, or about 70% of a time constant, but RC is 12, so I'm going to say times 12, and that gives me 8.318 milliseconds. So at T equals this, Q is equal to 1/2 E times C. So I want to box all this off. Actually, I don't want to box it. I'm just going to underline it so it can be something that comes in handy. Later, you'll see it comes in really handy. So now I'm going to finish with part D, and that is my job in part D, is to find out what I is at that time. So I of T is supposed to be E over R times, excuse me, this one's the one that just decays exponentially, E over R times E to the negative T over RC. So now I'm going to get I of 8.318 milliseconds, R, this is 0.6931 time constants. That is going to equal 1/2 E over R, basically, because we're going to take E over R and raise E to the negative 0.693, because T is going to be 0.6931 times RC, and then the RC is going to cancel out, so it's negative 0.6931. And if you put that in your calculator, you'll see it's exactly 1/2. So E to the negative 0.6931, it's actually not exactly 1/2. You have to carry all the digits, but you get 0.500. I've got 3 zeros after that, and then a 2 times E over R. And I don't think we did E over R yet, but that's I max. So what we see is I equals 1/2 I max at T, such that Q equals 1/2 Q max. So that's really the answer. This symbol right here means such that. Okay, so that's part D. Anybody have any questions on that? Part E is what time is that? And we already found that part. So I'm going to say E T such that Q equals 1/2 Q max is equal to 0.693 times tau, which we found was 8.318 or 8.32 milliseconds. So that's part E. Actually, I don't like that. I'm going to do it like this. And this is part E. And this is part D. Okay. All we have left is what is Q when I equals 0.2 I max. So I equals 0.2 I max tells us that excuse me, this is part F. So 0.20 times E over R is equal to E over R times E to the negative T over RC. You can see that the E over R cancels out, and I get basically, I'll take the log of both sides, the ln of both sides. The ln of 0.2 gives me negative 1.609. Is equal to negative T over RC. So the time is equal to 1.609 times R, or times the time constant. So I'll just say times tau. And at that point, we'll know Q of 1.609 tau is equal to, now I'm going to plug that into Q of tau. So I'm going to say 1 minus E to the negative 1.609, or excuse me, yeah, E to the negative 1.609. And that's going to give me basically 80%. So it's going to be 80% of the Q max. And that's the answer. Any questions on that? No problem, Haley. All right, so that's how you go about solving a charging a capacitor problem. You'll see next we have a potential to solve a discharging a capacitor, but I need to give you those equations. So in this case, it's really nice. The equations are just, and I'll write them in green this time for fun. I'm going to say that V across the capacitor is actually going to be, in this case, we don't necessarily know what charged it, because you could just be given a charged capacitor, right? So you didn't necessarily know that E was the voltage that you charged it to and all that good stuff. So it's best to have it in terms of Q and R0 and all that stuff. So if you use C equals Q over V, then you'll realize the voltage should be Q over C. So that's going to be, in fact, Q0 over C times E to the negative T over RC. So that's one equation. The charge Q is actually going to be Q0 times E. Oops, I didn't mean to write all that in blue. The charge Q, which we could also write as Q of T, is equal to Q0 times E to the negative T over RC. So we have that. And then finally, we can say the current I, that's going to, again, take off as soon as you flip the switch to the open part of the wire. In other words, the wire without the battery. And it's going to see a voltage lower than the positive side of the actual capacitor. So it's going to start running current around it. And that should decay over time, and that's going to in fact be I of T is going to reach its maximum when the entire voltage of the capacitor is across the resistor. So in that case, you could say The voltage across capacitor is Q over C, or excuse me, yeah, the voltage across the capacitor is Q over C, and then R is equal to, or excuse me, then I is equal to Q over RC. So it's going to be Q0 over RC times e to the negative t over RC. And this too comes from a differential equation, but it's a slightly different differential equation. Again, you can check my YouTube channel for derivations of it. You can also read them in your book, or you can ask me if you have any problems, but that's basically it. And all the graphs are going to look like that second graph I made because they're all exponential decay. So that's that. Now we've only got about 4 minutes, so let me quickly explain to you what you do with a galvanometer. So a galvanometer really is a type of ammeter, but it's usually very delicate. It's not, doesn't handle much current. In fact, this one's going to handle 50 microamps, and it's going to have an internal resistance of 30 ohms. And in fact, if you multiply 30 ohms times 50 microamps, you get the full voltage deflection of the galvanometer, which would be 1500 microvolts, or 1.5 millivolts. So that's really what that is. Now, to design an ammeter, what you have to do is you have to make the lion's share of the actual current go through a resistance that's really easy to go through, and we call it a shunt resistance. My wife works in the medical field, for instance, and they use the same terminology when they're talking about a hole from your right ventricle to your left ventricle of your heart, because when you're a baby, it's actually a hole from there, from where it used to not even be a 4-chamber thing, but a tube. And then as you grow older, that little valve that connects the two ventricles is supposed to close. It's called a patent foramen ovale. And if it doesn't close, what happens is when the right side of the heart squeezes, it's supposed to squeeze it out and send the blood to your lungs, but instead some of the pressure pushes the blood into the left ventricle, meaning that that particular ventricle is now getting unoxygenated blood and then sending that out to the body with less oxygen in it. So that's another example. So this red thing here is going to represent the ammeter, and what we're going to do is we're going to actually put the galvanometer, which is really including a little resistance like this, which in this case is 30.0 ohms, and then that's in with the galvanometer right here, and all of this is going to be in parallel with a shunt resistance, or shunt. And these would be the terminals of your ammeter. So that's why I put the red box around it, is so you know where the ammeter is. And this right here is technically the galvanometer. Now, because they're in parallel, that means that the V for the galvanometer is equal to the V for the shunt resistance. And the V for the galvanometer, of course, is 30.0 ohms times, when it's maximally deflected, it'll be 50.0 microamps. But that's also got to be equal to the current that goes through here. But the current that we want to go through here is really supposed to be 5 amps. So this is 5.00 amps. So I got to find out what current I need. And what I know is I have 0.10ths, hundredths, thousandths, 10 thousandths, 100 thousandths, and then millionths is a micro. So actually I need to go back one, and I put a 5 0 there, there, and there. And I do a subtraction. When I do that, I'm basically doing 5 minus 50 e to the negative 6. And that gives me 4.99995 amps. So in this case, I need 4.99995 amps times R shunt. And that allows me to say that R shunt is going to be 30 times 50 e to the negative 6. And now I'm going to divide that by 4.99995. And that gives me 3.00 times 10 to the negative 4th ohms. So what you'd have to do is you could put 10,000 3-ohm resistors in parallel, and that would give you the shunt resistance. But then you'd put that in parallel, of course, with the galvanometer, and that would make your ammeter correct. So that's it. And in fact, you get a full deflection of 50, which your meter would say microamps, but you would recognize that as really 5 amps. Okay. If you wanted to do a voltmeter, we're actually technically out of time, so you guys are free to go. I'm going to finish the voltmeter, and so that way you'll have it on the video, but you guys are free to go. Anybody have any questions before you split? That's the voltmeter problem, by the way. Any questions? Thanks for coming, everyone. Start doing your practice midterm or your practice second midterm so you can all kick butt and get an A on this midterm.
Professor Younger, I have a question for you.
Yeah, Various.
I made kind of a big mistake last week. Last Sunday, we had our test. I can't remember which test it was. I think it was the one for 24. Hang on. But last Sunday we had a test, and I actually
not a problem. I haven't been perfect, so I'm giving people a little bit of a break this semester. And you guys have had a time where you dealt with COVID and all that good stuff. So the least I can do is give you a little bit of extra time. I'm not even going to take off for you missing, even though you got a little bit of an advantage by having more days. So I'll just open it back up. If you don't see me open it tomorrow, send me a text message. So, and just remind me your name, the section number, and by then you'll know exactly what test you need to make up, and you can send that to me. I'm putting my cell phone number in the chat so that I don't have to say it on the interwebs. But here it is. So yeah, just send me a text if you don't see it posted by tomorrow. Just send me a text and I'll go ahead and do that. And I'm not going to take anything off, and I'll give you till Sunday to do it.
Okay, I really appreciate it. Thank you so much.
No problem. Have a good one, bud.
You as well. Okay.
Gavin, anybody else have any questions? It looks like it. All right. So what I'm going to do is go ahead and do this galvanometer design problem where I'm going to design a voltmeter this time. Now with a voltmeter, what you do is instead you put a resistance in series, and the vast majority of the voltage drop will happen across that. And we're just going to call it resistance R. So here's the solution. So again, what I'm going to do is, first off, I'll draw my circuit. So in comes a wire, and basically it's going to go into what I call my voltmeter, which will be this red box right here. And that wire is going to come in, and it's going to run through a resistance R. Then it's going to run through the 30 ohm resistor, and then it's going to run through the galvanometer, and then it's going to come out here. So the current is actually going through here. That's going to be some I. What we want, though, is 50 volts to basically be equivalent to 50 microamps. So luckily, what we have to do is we put voltmeters in parallel with the circuit, and then it forces it to be 50 volts. So what we really need is the entire voltage across here from here to here. This voltage needs to be 50.0 volts. Okay, but this voltage right here can only be 1500 microvolts, which I said was 1.5 millivolts, like that. So that means we can do some math. We can say 50.0, and then I can put a bunch of fake zeros after it, like this. And I need to take out the 1.5 millivolts. So what I'm going to do here is say 0.0. A millivolt would happen basically right at the third one. So this would be 0.1500. So if I do the subtraction, I get 50 minus 1.5 e to the negative 3. And that subtraction gives me 49.9985. So that's the volts that has to be across this part, is 49.9985 volts. So what I have is for this resistance R, I've got 50.0 times 10 to the negative 6 amps times R is equal to 49.9985 volts. So that gives me R is equal to 49.9985 divided by 50 e to the negative 6. And that gives me 999,970. Okay. Again, you wouldn't necessarily have exactly that kind of resistor laying around. You could get as close to it as you wanted. You'd actually want it to be, if anything, a little bit larger so it can handle even more than 50 volts. So you might go for a single mega ohm resistor, and then you go back and recalculate what a full deflection would count for, and then you use the scale accordingly. And you might even find that it would be more apropos to maybe use a 2 mega ohm or a 1.5 mega ohm, just because the math would work out with one of the scales. The way the galvanometer works is it'll normally have a scale that goes from 0 to the right would be positive 50, but 0 to the left would be a negative 50. But there might be another scale would be 0 to 5, and another scale would be 0 to 2 or 0 to 2.5 or something like that. So you can play with that a little bit, but that's basically it. And that's the end of chapter 26. So this ends chapter, not 36, chapter 26. And that's it. Thanks, everybody. Appreciate you coming. And now we're going to kill it. Bye, everybody. Bye-bye. Bye-bye.